Hello viewers, welcome back to the course on matrix computation and its application. So, in the previous lecture we have discussed one example and showed that the dimensions of range space and null space. So, today we are going to continue with that one. So, let us do this one. So, today I am going to discuss another properties of the corresponding system. So, if you remember that in the previous lecture we have discussed one example and we showed that the range of the given matrix. So, this was my matrix and we have discussed about the range space of A, range space of A transpose, and then we have also shown that the P matrix, the non singular matrix P. So, the row corresponding to the 0 rows in the echelon form, and then using this one we have showed this relation that range space of P to T is equal to the null space of A transpose. So, the same thing we are going to discuss now. So, it says that suppose we have a matrix A that is M cross N, and let the rank of A is equal to R, and let we have a matrix P that is given by P1 and P2 as discussed in the previous lecture be a non-singular matrix such that PA is equal to U, that is the row echelon form. So, this will be definitely some matrix C that is R cross N, and this will be 0 because the rank is R. So, this matrix is going to have only non-zero rows, that is R in number, and N is the number of variables. So, this is there where U is in row echelon form. Then we are going to have one relation, and this relation is that the range of A can be written as null space of P2, this one. So, where this is my P2. Earlier we also discussed that N A transpose, that is a range space of P2 transpose. So, this is we have discussed in the previous lecture. Now, I want to discuss this one. So, as we have done previous example. So, from there I will, so this one already we know. So, P2 I am just going to get what is the P2 there. So, basically if you see, then my P2 is minus 2 1 0 0. So, that is my P2. My P2 is basically this row minus 2 1 0 0. So, this is my row vector. Now, I want to find what will be the null space of P2. So, basically we are going to write P2, that is minus 2 1 0 0. So, it is a row vector, that is basically 1 cross 4, and then I will apply over. So, this will give me this into I am applying over the element 4. So, suppose I am taking it as a x1, x2, x3, x4. So, it is basically 4 cross 1 and then it should be equal to 0, because whenever we are going to deal with n a, it means we are going to deal with this system. So, I am going to deal with the null space of P2 implies that P2, this is our matrix that of dimension 1 cross 4 with this the number of variables, and that is putting equal to 0. So, from here I can write this as a minus 2 x1 plus x2 equal to 0. So, I am getting only one equation from here. So, this one we have done, only one equation is there, and my matrix was from R5 to R4. So, that also we have to keep in mind that our matrix was 4 cross 5. So, moving from R5 to R4. Now, this is our equation. Now, from here you can see that x3 and x4 are basically free variable, because that are multiplied by 0. So, from here I can say that this is the equation number 1, and x3, x4 are free variables. So, from here I can write down. So, now from the previous matrix we came to know that the rank of A is 3. Okay. So, and the range of A is this one. So, it is made up of this one. So, this one we are going to do now. So, from here I can say that my x1, or maybe I can write my x2 can be written as 2x1. So, this relation I can write. X2 is becoming equal to this one. So, from here I can write that my x2 is equal to 2x1, okay, and x1 is always there, and x3, x4. So, this is my vector I am going to have. So, that vectors can be written as, because this vector is basically I need to find the values of x1, x2, x3, x4. So, x1, x2, x3, x4 can be written like this way. So, from here I can write, I can take the x1 common. So, it will give me 1, 2, 0, 0 plus I can write x3, that is 0, 0, 1, 0 plus x4, that is 0, 0, 0, 1. It means that the null space of P2 is spanned by this set of vectors 0, 0, 1, 0 and 0, 0, 0. And you can check that this set is linearly independent and is, so this will be the subspace. So, it belongs to the set R4. Okay, and this will be, so now if you see from here that in this case my range space of A is spanned by the element 1, 2, 3, 1, 2, 4, 6, 4 and 1, 2, 6, 3, but there are 3 number of vectors are there and they are linearly independent. The same thing is coming here, only the thing is that we have the same number of vectors, but these vectors are not the same as the we have got in that range space of A. But so in this case we can say that the basis vectors has been changed, but the dimension is same. So, from here you can check. So, from here you can imply that the null space of P2 is always equal to, so this is can be written as range space of A. So, this one we have done. Okay, so this way we can write down these things. So, after doing this one, now we going to start with some another things, that linear independence and matrices. So, suppose we have a matrix A that is M cross N matrix. Now, first one, that each of the following statement is equivalent to saying that the column of A form a linearly independent. So, this word can be written as Li. So, linearly independent set if the null space of A contains only 0 element. So, each of the following statement is equivalent to saying that the columns of A forms a linearly independent set. So, because in this case we have a matrix A M cross N. So, I know that it is going to have n number of columns and m number of rows. So, the columns of A forms a linearly independent set. It is equivalent to saying that the null space of A is 0 and the rank of A is going to be equal to n, the number of variables. So, this is a 0 null space. Second one, now I can talk about rows of A are linearly independent set. It is equivalent to saying that null space of A transpose is just the 0 element, and the second one is that the rank of A transpose is equal to m, and m is the number of rows in that given matrix. So, now the third case is that what will happen when the matrix A M cross N is a square matrix. Square matrix is when M is equal to N. Then A is non-singular. So, that is equivalent to saying this is equivalent to saying the first one is that the columns of A forms a linearly independent set. So, all the columns of A are linearly independent to each other, and the second one is that the rows of A forms a linearly independent set. It means that the rows of the matrix is also linearly independent to each other. So, these things we have to keep in mind. Now, using this one, so it is very clear. So, I can discuss the proof. Now, column of A forms the linearly independent set and the rows of A form the linearly independent sets. So, we can say that suppose I have the matrix A, that is M cross N matrix. Now, so I am saying that the columns of A are linearly independent. So, this one I am doing this one, saying that the column of A are linearly independent, that is equivalent to saying that the null space contains 0 or the rank is equal to n. So, this is the proof for first one. So, I am saying that the column of A are linearly independent, which implies that, so I have a matrix and that matrix is basically, it has the column. So, that column I can write as A1, A2, An, n number of columns, and these are the linearly independent. So, these are linearly independent means that if I take the linear combination alpha 1 A1 plus alpha 2 A2 alpha n An is equal to 0. So, it is there. Then since A1 A2 or An are Li, which implies that the set alpha 1 alpha 2 alpha n that belongs to Rn belongs to, so this is belongs to Rn. So, it is going to be that, so if it is a linearly independent, then I can write even that alpha 1 is equal to alpha 2 alpha n all are 0. So, if all are 0, then from here, which implies that the set alpha 1 alpha 2 alpha n belongs to null space of A. But in this case all the vectors are linearly independent and showed that this alpha is are 0. So, from here I can say that null space of A will be only 0 element, because all the alphas are 0. So, this is okay, we are able to show this one, that the null space will contain only 0 element. And now, from here you can say that this is equivalent to saying that the matrix. So, now null space of A contain only 0 element, which implies that the matrix A is non-singular. If it is a, now these things I can say only when it is a square matrix. So, I can note like this one. So, from here I can write that, from here I can say that the rank of matrix A is equal to n. So, that I can say, because null space contains only 0 element. So, I can say that the rank of the matrix will be n. So, that is rank of A is n, because if it is a square matrix, then I know that the rank of the matrix will be A n, and then it will be non-singular. So, this the same thing we can write down. So, similarly can prove the other two. So, this is the other two properties what we have, or the statements. So, other two statements, because in that case we have to deal with only rows. So, the rows of A are linearly independent, then the same way we can write down that the null space of A transpose will be 0 and the rank will be equal to the number of rows. And if it is a square matrix, then we can say, because if M is equal to N, now if M is equal to N, then rank of A is equal to N, which implies that matrix A is non-singular. Also, the rank of A is equal to the rank of A transpose. So, that we already know, because we take the matrix A, find the rank, then you just take the transpose of that matrix and then again find the rank, they will be same. So, this we already know, the rank of the matrix and its transpose are always same. So, these things we are using this one. Now, so I want to use these statements for solving some real applications, that if the null space contains only 0 element, then this is true that the given columns are linearly independent, or the corresponding rows are linearly independent, or if the matrix is a square matrix, then it will be a non-singular. So, these things we are going to use for discussing some important things. So, the first thing we are going to discuss is very important topic, and that is called diagonal dominance. So, a matrix A, so that is of order n cross n. So, I am talking about the square matrix, is said to be diagonal dominant or in some books sometime it is also written as also called strictly diagonal dominant. In some books it is written as strictly diagonal dominant. So, a matrix A is said to be diagonal dominant if I take the elements at the main diagonal taking the modulus value. So, if it is greater than equal to summation A I j magnitude j is moving from 1 to n and I is not equal to j for each I that is equal to 1 to up to n. So, this is called the diagonal dominant matrix. For example, suppose I take the matrix A, that is I may take 3 cross 3. So, in this case suppose I write here 4 minus 1 minus 2 and it is minus 5 1 3 and 1 2 and this is suppose I am taking minus 4. So, in this case if you see then this is my diagonal elements, and from here I can say that the 4 is greater than -1 plus -2. So, that is in the first row I am talking about, and the second row we are writing diagonal elements. So, -5 modulus value is greater than 1 plus 3, and similarly -4 is greater than 1 2. So, everywhere it is coming. So, it is called diagonal dominant matrix. But suppose I take another matrix B, and if I write the same matrix 4 -1 -2 1 -5 3, but here suppose I write 2 2 -4. So, in this case if you see that starting from here, then in this case -4, that will be equal to 2 plus 2. So, in this case we are going to have only equality sign. So, this sign is not there. So, in this case we say that it is not diagonally dominant. So, this type of matrices are playing a vital role in numerical analysis or for the convergence of some numerical methods or iterative methods. So, based on this one I want to show. So, now we know that the iterative methods like Gauss-Jordan or Gauss-Seidel methods, the sufficient condition for convergence is diagonal dominant matrix. So, iterative methods like Gauss-Jordan or Gauss-Seidel, we know that the sufficient condition for convergence is that the matrix should be diagonal dominant. It means we have a matrix A that is equal to x equal to b. So, this is a system of equations are there, and this is suppose n cross n. So, I know that this type of system can be solved with the help of, for example, we have done Gauss elimination. So, in the Gauss elimination, if you see, we use the pivoting. So, pivoting is basically to have the largest element at the diagonal places. So, this type of things are also related with the diagonal dominant matrix, and others are iterative methods. So, this is a direct method basically. And another is the iterative method. So, iterative method is like Gauss-Jordan or Seidel. So, this type of methods are, if we apply, we are not sure that whether we are going to have the solution or not, but in this case we are going to get the solution if the matrix is diagonal dominant. So, that means that is called the sufficient condition, that if the matrix is diagonal dominant. So, if A is diagonally dominant, if A is diagonally dominant, which implies that Gauss, Jordan or Seidel are convergent. But the converse is not true always. If the methods are converging, that also does not mean that the matrix should be diagonally dominant. But if the matrix is diagonally dominant, then definitely it is going to converge. So, these type of things are very important to deal with the iterative processes for solving the system of equation. So, that things is we are going to discuss in the next lecture. So, let me stop here. So, in the today lecture we have discussed about another properties of that is related with the matrices, that if the null space of the matrix corresponding matrix is only the 0 space, then we can have that the given matrix is going to have the columns are going to be linearly independent or the rows are going to be linearly independent. And then we have also discussed another definition of diagonal dominant matrix. So, we will use this one to show some properties in the next lecture. So, thanks for watching. Thanks very much.